Hello, and welcome to the Badger Talks podcast, the podcast that shares interviews with experts from the University of Wisconsin-Madison community about their work, research, and a little bit about what they're like as people, too. I'm your host, Buzz Kemper. Today, we're focusing on astronomy, and I'm happy to have as my guest Assistant Professor of Astronomy Michael Maseda of UW-Madison to talk about his work with the James Webb Space Telescope. Note that Professor Maseda sometimes refers to the James Webb Space Telescope by its initials, JWST. So, Michael, I'm really excited to jump into this because I don't know anyone who has actually used the James Webb Telescope. And you've been part of this team. So please tell me how this came about, first of all. How did you get hundreds of hours on this wonderful instrument?
So I worked as part of a team of scientists that worked with the engineers that designed one of the instruments on the telescope. So this was done by the European Space Agency, and they have a lot of expertise on building hardware, and so they wanted a group of scientists to basically use it and demonstrate its capabilities, right? Because particularly at the beginning of a big mission like this, right, we're hoping JWST is going to be 10, 15, 20 years, it's really good to show what it can do early on, right? So scientists have an idea about the kinds of things that are possible or, difficult or easy. And so we were tasked essentially to create basically the sort of dream survey that one could have with this big chunk of time. And all of us were really kind of like-minded about this. We identified, this particular instrument as being really, really good at telling us about the distant universe, okay? Because there's a lot of different questions. Like a telescope like JWST or like Hubble can answer a lot of questions in a lot of different areas of astronomy, but the thing that we thought would be most impactful was looking for very, very distant galaxies. Now, the reason that we do that is because when you look at something far away, you're looking back in time because the light takes some amount of time to reach us. And so by looking further and further away, we're looking back in time. And so we want to know what the universe looked like just a few 100 million years after the Big Bang, right? What were the first stars and the first galaxies like?
Mm-hmm. And I love that you're explaining that we are looking back in time, because that occurred to me as I have read various stories about the Webb Telescope and the Hubble Telescope, is that you are basically like historians, you're looking, deep history. That's amazing. So I have a million questions. Let's start with this one. What is the difference between the James Webb Telescope and the Hubble Telescope?
The main difference is that the James Webb Telescope looks at different wavelengths of light. Mm-hmm. So different wavelengths of light, for example, are different colors, right? If you're familiar with the colors of the rainbow, red are the longest wavelengths, violet are the shortest wavelengths, and our eyes just interpret different wavelengths of light as different colors. Mm-hmm. Now, there's light that's longer wavelengths than red, and that's called infrared, and that's what James Webb sees. So if you've ever looked at like a thermal camera or thermal imaging camera, those are infrared pictures. And the reason why that's interesting in this particular context of distant galaxies is because not only does light take a long time to reach us from these distant galaxies, but in the time it's been traveling towards us, the universe has been expanding. And so the light gets stretched out. Mm-hmm. So light, for example, from a star like our sun, right, it's mostly kind of like yellow. We see that. Mm-hmm. But if that light is traveling for 1 billion years and the universe is expanding, the wavelength gets stretched out to longer wavelengths. And so we expect that really distant galaxies, essentially, even though all of their stars are similar to our sun, it's all going to appear in the infrared. Mm-hmm. So a very distant galaxy would be completely invisible to our own eyes, right? We wouldn't see any light. It would all be coming in infrared light. So that's the main difference. Mm-hmm. And in addition to that, there's some overlap as well. It can see red light, for example, like Hubble can, but it's just a bigger telescope as well. So it's about 3 times larger in diameter, and that also means that you can collect more light, so you can see fainter things in the same amount of time. It's
a fascinating thing. My understanding is that you were asked, what would you want to do if you had these hundreds of hours with this telescope? What would you want to look at? What would you want to find out? So what was your answer?
Yeah, so we decided to do 2 different things, actually. So the first one was, let's take all of the galaxies that we knew about with Hubble and let's actually look at them in more detail than we could have before, right? So one of the things that Hubble can't really do is Hubble can take pictures, but Hubble can't take spectra. Now that's also, I think, one of the big differences between JWST and Hubble is JWST has the ability to take spectra. And so what that is basically breaking up the light from a particular object into its individual wavelength components. And the reason why that's interesting is because things like certain gases, for example, if they're really hot, they glow at very specific wavelengths. So they don't produce a continuous emission of color, they produce light at very, very specific wavelengths. And that's really important when you're talking about a distant galaxy, because if you can break up the light into the different colors, you can basically kind of like take its fingerprint, right? You can say that the gas inside this galaxy or the stars inside this galaxy have a lot of oxygen or a lot of carbon or, other elements as well. And this is kind of like a clock, because at the beginning of the universe, we just had hydrogen and helium. So if you've ever heard anyone say that we're all made of stars or stardust, anything that's not hydrogen or helium has been produced inside stars. So the very first stars were just hydrogen and helium over their lifetime, and as they died, they produce heavier elements like carbon and nitrogen and oxygen and so on. And so the specific ratios of all of these elements tell us basically how many times and what kinds of stars have formed in a galaxy, in a completely new sort of regime than what we could have done before.
And so you're learning about the age of the galaxies, and you're learning about the relative position of the galaxy, about how far away it is. Are you also able to tell how fast they're moving in this expansion? Are they, in other words, are the ones farther away from us moving faster or at the same rate?
So they're moving faster away from us.
They are?
Yeah.
Okay.
So you can measure that.
What does that tell us? Is that another, sort of brick in the wall building up the argument for Big Bang? Or is it more than that? That fascinates me, that the speed increases as it gets away from us. What does that mean?
It is, I think, as you described it, another sort of, brick in the wall of this whole picture that we have, because, putting together the theory of how the universe formed is very hard.
Yeah.
And in particular, we haven't had observations in this very early epoch, right? As you say, right? We're trying to understand what happened in the very early times, and maybe it was different than what we were expecting. So this is the first time that we're actually able to do that, to kind of loop back around. We haven't seen anything yet that's really challenged our theories of the universe and of the Big Bang. I think everything is holding up just fine, after 1 year of observations with this telescope.
What, if anything, has surprised you the most from your work with JWST?
The most important thing when you have a new facility of any kind and you're looking at a new parameter space, the most important thing I think going into it is don't just look for things that you understand, right? If you just see things that are confirming everything that you thought before, you're not learning anything, right? So be prepared for a surprise, keep an open mind. And so I like to get excited about the things that we can't really understand, right? And the thing that we're having a little bit of a hard time with now is how big they are. How many stars do they have? Because one would expect the very first galaxies that formed in the universe probably didn't have very many stars. They haven't had a lot of time to build up their total stellar mass. And it would take millions and billions of years for them to grow larger, to form new stars. To form a star takes several million years, so it's a long process. When we're measuring the light output from some of these distant galaxies, there's basically evidence that there's more light than we were expecting, which means there are more stars than we were expecting. And it's not a totally well-formed issue at the moment. There's some tension with some of the models that we have. So I'm not going to come here and say that like our idea about the universe is broken. I think some people have made these claims and said our idea about dark matter must be wrong because these things are too heavy. There's a lot of systematics and a lot of details that we're still working out, but I think there is some indication that galaxies probably formed earlier and faster than we had thought before.
That is interesting. And so I assume that there are galaxies still being formed and galaxies still dying, and they have a lifespan, right?
Yeah. So our Milky Way galaxy is alive, right? And when we say alive, we're referring to new stars are being born inside of it. So stars form out of gas, clouds of gas that condense because of gravity. They get pulled together, and once it gets really, really dense, it starts to heat up, and then you have nuclear reactions happening, and you have a star forming at the center of this collapsing gas cloud, right? Now, some galaxies have no gas, right? They've used all of it, right? So the analogy we use is like it's fuel, right? You take gas and it's the fuel and you make stars out of it. Some galaxies have run out of gas, and there's different reasons for it. But there are a lot of galaxies that don't make any new stars, and we can sometimes call those galaxies dead galaxies. So galaxies are in the process of dying. All of them. They'll run out of gas eventually and everything will die. And it goes back a little bit to what I said before about these, slight interesting puzzles for, big, heavy galaxies early in the universe. We've also, not quite at the very, very distant, very early times, but we've seen galaxies dying now with JWST. We've seen these dying galaxies at times that are also a little bit earlier than we were expecting. So it seems like the whole life cycle of galaxies maybe started a little bit earlier than we thought and started to happen a little bit faster than we thought.
About how long does the Milky Way galaxy have in our best estimate at this point? Where is it at in its life?
It's probably late middle age.
Okay.
It's still got some time left. The big thing that's going to happen to the Milky Way, which is not necessarily something that happens to every galaxy, our nearest neighbor, the nearest big galaxy to us, is the Andromeda galaxy.
Yeah.
And we're moving towards it. And I don't know the exact amount of time it's going to take, but at some point in the not too distant future, we're going to smack into Andromeda. And that's going to cause a whole bunch of things to happen. One of the things...
Oh, do tell.
if there's some gas, and there will be some gas in both of these galaxies, when you throw two galaxies together, that gas tends to form a lot of stars very quickly. So you have a big, what we call a starburst. You'll form a lot of stars very quickly, but that also then means that there won't be a lot of gas left over after that. So it will form stars very efficiently for a short period of time, and it'll kind of burn out after that. So the idea would be, once we merge with Andromeda, there'll be fireworks for a few 100 million years, and then the whole system will die, essentially.
Wow. Will the planets that are currently in both those galaxies survive the impact? I mean, I know that there's more space than there are planets, so I'm not assuming that they're all going to crash into each other. But just the fact that the galaxies themselves are converging, is that going to damage or destroy existing planets or stars in either one?
So... yeah, as you say, for the most part, there's so much space between stars,
right,
for
I think
example.
of them as like atoms. There's a lot more space than there are,
Exactly. So two galaxies merging is almost like if you had two gas clouds running into each other, right? The atoms don't actually hit each other in those cases.
Right.
And so the stars won't hit each other. You may have cases where a star, even if it doesn't hit another star, it'll be close enough that there'll be some gravitational interaction. And so maybe some things will slosh around a little bit.
Okay.
But for the most part, I think most things will still be. So our sun, for example, will probably not smack into anything else.
Okay.
If the Earth is still there at that time, it'll probably stay in the orbit. But we can't know that for sure.
Okay.
Yeah.
About when will this happen? I mean, obviously it's not going to be like next week, but when will this convergence happen?
I think our best estimate now is it'll be about 5 billion years before Milky Way and Andromeda hit each other. It'll take a long time for it to finish merging. But yeah, about 5 billion years or so for it to start.
Okay, so none of us have to fasten our safety belts right now.
I don't think so.
Wow, such incredible stuff. Is there any reason to believe that there are any dents in the Big Bang theory, or is that still the best explanation we have for where it all came from?
So that's the best theory we have. I don't think anything really has caused us to question that. We still don't have a very good understanding of the very, very, very beginning. So like the first sort of 10 to the minus 30 seconds of the universe. That little bit of time is very, very hard to understand. But everything really after that, we have quite elegant theories and theoretical models that kind of explain and make predictions that can be tested. I think that's the other thing. We don't, as astronomers, we don't run experiments in the way that a chemist would. Right? We don't control what happened in the universe. We can just observe things. This idea is that essentially of all of the total stuff in the universe, only about 4 or 5% of it is stuff that we know, like atoms, essentially, right? Yeah. There's a big component of the universe, and that's dark matter. And it's strange to say, but we think we understand dark matter reasonably well because it interacts gravitationally. And so even though you can't see it, you can measure its influence on things via gravity. And then there's this whole question of dark energy, which is this other thing. We don't understand that very well at all.
Right.
70% of all of the energy in the universe is contained in this dark energy. That's a different thing.
What would you want listeners to know for which I have not asked the right question?
I think one of the important things about all of this, this whole JWST mission is a joint partnership between NASA, the European Space Agency, and the Canadian Space Agency.
Right.
So, and even beyond that, right, scientists from all over the world use this facility. So it really is one of these things where there's a huge investment, particularly on the side of NASA, and it has benefited science around the world. And so I think it's so exciting. We focus mostly on my research and talking about these distant galaxies, but there are really important contributions that JWST is making in all parts of astronomy. I think in that sense, it's quite unique because everyone wants a piece of the action. Everyone wants to use JWST to answer their, a question in their field because it is such a sort of multifaceted telescope. There's a lot of different instruments on it, and everyone has really been invested in the success of the mission. So we're kind of still ironing out some of the kinks, but I really am excited for the next 10 plus years of this mission because it's going to touch every field of astronomy. I think is going to be touched by this, and scientists from around the world are going to be doing this. So it's great. It's great for all of us. I think that we can have this telescope and we can all use it.
Just one final question. When you're not studying this stuff, let's just get to know a little bit about who you are as a person. Who are you outside of your scientific life?
So I'm a big cyclist. So I just moved to Madison 2 years ago,
great.
and I'm loving the bikeability of the city. I'm liking all the bike trails around, so I can get on my bike on the weekend and make a really nice day out of it. So that's been great. I'm originally from Florida, and so adjusting to the Madison winters has been a challenge. But I think I like cold weather. I think if I'm prepared for it. I used to play hockey. I think I'm going to start playing hockey again.
There you go.
That'll be fun to do. So so still kind of getting my feet under me in Madison, but I'm loving it so far.
Welcome as a 2-year Madisonian, and thank you so much for the conversation. I feel really a lot smarter about what this stuff is all about.
Great. Yeah, thank you so much.
You've been listening to the Badger Talks podcast. I hope you enjoyed my conversation with Professor Michael Maseda. Please browse our previous episodes for other topics that may be of interest to you. The Badger Talks podcast is a creation of UW Connects and produced at Audio for the Arts recording studios in Madison, Wisconsin. Our music is composed by Bill Purdy and performed by the UW Marching Band. I'm Buzz Kemper. Thank you for listening.